So let's go ahead and start this video on 4 different epoxide reactions. So these are all epoxide reactions, okay? So let's go ahead and figure out where our epoxide is. We can see it right there. Let's go ahead and figure out the conditions under which we're acting. So what conditions are these under? So I see this NaOET. This definitely has a plus charge, which means this entire molecule, let me go ahead and actually do that in blue. This entire molecule right here has a negative charge. So that's a pretty basic condition, right? We have a negatively charged ion, nucleophilicity and basicity correlate pretty well. So that's going to be a strong nucleophile and a strong base. We have an aprotic solution, which isn't that important, but we're hinting at an SN2 type reaction, right? We have a strong nucleophile, strong base, an aprotic solvent. This is looking like an SN2 type mechanism, okay? So now we got to figure out which carbon is it going to attack. Is it going to attack this carbon or is it going to attack this carbon? Well, don't forget, under basic conditions where we have a strong nucleophile and a polar aprotic solvent, it's always going to attack the less substituted carbon, aka this one right here, because you have less steric hindrance when it comes to a backside attack, right? So less substituted carbon is this right side one over here. So what's the first step? The first step is this oxygen takes those bonds, right? And then what happens? And then our nucleophile comes in, OET has a negative charge, this has lone pairs, and it attacks the carbocation that's formed. So I'm just gonna take this step by step and I'll draw out each step. We're gonna have positive charge formed here. We're still gonna have a wedge shape because that's not the carbon being attacked, so that stereochemistry is not affected. We should have an O negative, and we should have a methyl group, this one right here, okay? In the same place as it always was. Now, the next step is the nucleophile attacks, right? OET attacks right there. And then we get this product. Let me just draw it out right here. Oh, that was horrible. 1, 2, 3, 4, 5 carbons. Same thing, wedge, dash. Still have a negative charge on that. That's going to be important for later on. But this time, we're going to add this OET, right, via a bond. But what kind of bond? Don't forget, in epoxide reactions, the stereochemistry always is inverted. So if this was a wedge, we now have a dash. I'm going to draw it in blue. Blue is the color of my nucleophile. OET. Okay? So we're almost done. We have our inversion correct. We have our the stereochemistry of this left side correct. But we still have one more step, right? Water is in this reaction for a reason, because the lone pairs on this oxygen are going to attack that H. Because that oxygen, although it is fairly electronegative and it can carry that negative charge okay, it can carry it well, we still want to protonate it if we can, because alcohols are more stable than just a negative oxygen charge. So we're going to have this molecule right here. We're going to have, again, a wedge, oxygen, OH. Let me actually draw that in green so we keep the color going. Oh, why is it not going green? Green, so we keep the color going. This should still be wedged away. It's a methyl group, okay? And then we should have this OET attached to the end, okay? So this should be our final product. Okay, perfect. Now to the next word. Oh, this is interesting. We have a Grignard reagent, and this is actually acting as the nucleophile. So we have these two parts to our nucleophile. We have this part, which is negatively charged, and we have this part, which is positively charged. So our nucleophile is right over here, right? Our nucleophile is right over here. And then this is obviously in a drying agent, and the water comes next. Remember, when you're using Grignard reagents, you always want to do the water in a second step. This drying agent has to always be there, okay? So let's first figure out which carbon we're going to attack. Are we going to attack this carbon, or are we going to attack this carbon? Just by the looks of this pretty symmetric molecule, right? It has a line of symmetry right here. It doesn't matter which one we attack. They're both going to be the same types of carbons. So we can just pick one right now. Pick one at random. Let's choose that one. So I'm going to draw this out real quick. It should look like this. And then straight line with 2 carbons coming off of it. This has a positive charge. Well, what's going to attack it? Obviously, this Grignard reagent is CH2, CH3, minus charge. It's going to come in and attack that carbocation, right? And we're going to end up with oxygen, negative, boom, boom. And then we have this product formed. Okay? Then our next step, like usual, is going to be to protonate that oxygen. The lone pairs on this thing come and attack that oxygen, and you end up getting an OH plus this molecule right here. Oops. That should be our product for the second problem. These are all pretty similar mechanisms. The only important part is that we really understand which carbon we're attacking and why. Okay? So what kind of a reaction is this one going to be? This one's kind of tough, right? We have lithium aluminum aluminum hydride, but it's not really hydride, it's deuterium. That's not that important. These are just these act like negatively charged hydrogens. So would this be acidic or basic conditions? Well, if I'm not mistaken, these should be basic conditions because that aluminum hydride carries a negative charge, which is going to be fairly basic. It's going to want to pull other hydrogen. It's either going to want to pull other hydrogen atoms towards it and create hydrogen gas, right, H2, or it's going to want to react with other slightly positive molecules like carbocations. Okay, so let's go ahead and see what happens. So this is basic condition, so it's going to attack the less substituted carbon. So in this case, which bond's going to break? That one or that one? In this case, the less substituted carbon is over here, and this one's the more substituted one. So this less substituted one's going to break. So we're going to break this carbon off. And what is that going to form? That's going to form phenol, like that, straight line. And we're going to get a wedge with an O on it, and then obviously another methyl group over here. Again, negative charge, you get a positive charge. What's going to attack it? Well, the one of these D's is going to attack it. It should be a D minus, right? A D minus is going to attack it right here. And what you're going to end up with is a very similar mechanism to all the ones we've been doing. It's going to look like this, plus a deuterium. And then we're going to have this wedge that's still over here. You get an O minus and that methyl group. Actually, look at a mistake I just made earlier. I drew a straight line here. This should not be a straight line. This was originally a wedge, so now it has to be a dashed line. So it should be a D, okay, with a dashed line. The stereochemistry has to be inverted. That is just a rule when you're working on epoxide reactions, okay? And then again, the final step is always this water has to protonate that oxygen. Again, lone pairs like we usually see. Go ahead and redraw it up here. And our final product should look like this. Straight line. You have this dashed product, the D on it. Then you have the methyl group, and it's very important for us to draw these wedges. We have this wedge right here with an OH on it, and this is looking like it's going to be our final product. Okay, cool. We've got 3 out of the way. Let's do this last one. Okay, so again, what kind of conditions are we in? It's looking pretty basic. We have an OH minus, that's a very strong base. We have a protic solvent right here, DMF. And then we have H2O as we usually do. Again, the first question we ask ourselves is, which carbon? Do we attack this carbon or do we attack this carbon? And again, in this case, they are both identical, right? They are both identical. So let me go ahead and draw this again. I'm going to draw it slightly tilted only because I like drawing these cyclohexanes in this position. So I'm just going to redraw this molecule on the right side. It looks like this. Wait, I didn't draw my... It looks like this. Okay, these two are the exact same drawings. I just kind of shifted it 90 degrees to the right. Okay, now let's go ahead and see what happens. Which carbon is it going to detach from? Again, does not matter because they're both the same. So I'm just going to redraw this really quick. It should look like this now. The carbocation is right here, and we should have a O minus. Next up, what attacks this positive charge right here? Of course, this OH, which is negatively charged. This is positively charged. This OH has 2 lone pairs that are going to come in here and attack. Then we're going to form what? Then we're going to form this molecule. We're going to form this, still a negative charge. And now we have a inversion of the stereochemistry, right? So make sure you draw a wedge instead of a dash. Over here, it was a dash, and now we have a wedge. Okay, so now we have an OH. I'm going to draw it in blue to keep the colors. Ooh, this is looking pretty interesting. This is looking like we're going to have two alcohols. Now after the H2O is added, right, this is the step where this is finally coming into play. We're going to have an H2O here. This negative charge is going to attack one of those hydrogens, and we're going to end up with a final product that looks something like this. Oop, it's not a benzene. That looks like this. O, you just draw the H in the correct color, and then has a wedge, which is very important, and an OH. Okay, so there's 4 problems, all under basic conditions, that shows us how to do epoxide reactions. They're all pretty similar. They all follow a few steps. 1, figure out which carbon is being attacked. Okay, then attack the carbon with the nucleophile. Wow, this is being tilted like crazy. Then attack the nucleophile, and the last step is protonate O- to form, and let's try to straighten this out, to form an alcohol. Okay, these 3 steps are essentially the key to solving these problems. Okay.